When a modern fighter jet like the LCA Tejas pulls up into a steep climb, the external aerodynamic pressures acting on the airframe are immense, pushing back against the control surfaces with thousands of pounds of wind resistance. Yet inside the cockpit, the pilot maneuvers the aircraft through these violent physical forces with completely effortless two-finger movements on a small control stick. Early aviation required pilots to physically fight the wind using raw muscle power, hauling on thick steel cables that were directly wired to the aircraft's flaps and rudders. Curiously, today those cables are gone. That leaves us with a fascinating engineering problem. How exactly does an aircraft take a gentle digital nudge on a joystick and translate it into the massive physical force needed to move heavy wings at Mach 1? The solution is fly-by-wire. By severing the direct mechanical link between the pilot and the plane, modern jets rely entirely on a highly choreographed handshake between digital logic and raw mechanical power. The process starts the precise moment the pilot moves the stick. That physical action is immediately recorded by sensors and digitized into raw data. That data rushes straight to the flight control computer. The computer instantly evaluates the requested maneuver against the aircraft's current speed and altitude, checking the math to ensure the turn won't push the airframe outside its safe flight envelope. Once the computer verifies the math is safe, it approves the command and fires a digital signal down a heavily shielded physical wire array. In military applications, this routes over a strict communication protocol called the MIL-STD-1553B databus. Up to this exact millisecond, the pilot's command exists purely as a mathematical instruction moving through a wire. It currently possesses absolutely zero physical power to steer a multi-ton jet. To translate that math into muscle, the signal hits a highly specialized component called the electro-hydraulic servo valve, or EHSV. In this simplified EHSV cross-section, an electrical pulse from the databus drives a microscopic internal torque motor. That tiny motor turns, physically shifting an internal spool sideways. This clears a specific pathway, redirecting fluid into a newly opened channel. That microscopic slide inside the valve is the exact moment digital code converts into physical intent. To scale the valve's tiny movement, the system relies on Pascal's law. This dual syringe model demonstrates force equals pressure multiplied by area. Pushing down trapped fluid in a small area transfers the exact pressure to a larger area, massively multiplying the outward force. Modern aircraft take this tabletop physics concept to an extreme scale. Engine-driven pumps constantly compress the aircraft's hydraulic fluid, sustaining intense system pressures between 3,000 and 5,000 pounds per square inch. When the EHSV shifts, that intensely pressurized fluid rushes into a specific chamber inside the actuator. The fluid expands violently against the surface area of a heavy steel piston, physically forcing the rod outward. The pressurized fluid operates as a liquid lever. It successfully takes the weak electrical impulse sent by the pilot and scales it up into thousands of pounds of mechanical lifting force. But the computer needs absolute proof that the physical action occurred. That requires a final component, a position transducer mounted directly onto the exterior control surface. The moment the hydraulic piston extends and physically tilts the wing flap, the transducer takes a real-time measurement of the flap's new physical angle. It immediately fires that specific location data back up the databus to the flight computer. This successfully closes the loop, confirming that the pilot's original instruction was physically executed. This entire sequence, the stick movement, the flight computer validation, the hydraulic valve translation, the physical piston strike, and the sensor feedback, completes its cycle continuously in a matter of milliseconds. High-performance flight works because of this strict, invisible architecture. Code, voltage, and heavily pressurized fluids operate in a continuous, perfectly timed loop to keep the aircraft flying.